For today's lesson, we are going to be covering section 5.2 of our text, namely one-to-one and onto functions. We have seen this material previously. In linear algebra, we see one-to-one and onto functions, namely linear transformations, which are the subject of study. In calculus, we study one-to-one functions in order to define what the inverse function is. So if you recall back to how does one define the logarithm, inverse trigonometric functions, right before we talk about the notion of one-to-one. But now we are going to be covering it from the perspective of set theory. So let's begin with the definition of one-to-one and onto. So we have a function from a to b, where here a and b are sets, and we say that f is one-to-one if there does not exist an a1 in the set A, and such that there exists an a sub 2 in A, and with the property that f of a1 equals f of a2, and a1 does not equal a2. Now, Bellman, as is his habit, has these definitions written in its logical form. In just a moment, we're going to talk about how this translates to the notion that we are used to from our previous courses, namely a function is one-to-one if every input has exactly one output. And so every input has exactly one output. And so this is a way of keeping in mind what it means to be one-to-one. And similarly, a function f maps onto b, or just is onto b, if for every b in b, there is some a in the set A, such that f of a equals b. A better way of perceiving these definitions is via the following theorem, which gives us an equivalent way of understanding what it means to be one-to-one and onto. So f is one-to-one if and only if for every a in a1 in the set A and every a sub 2 in the set A, if we have that f of a1 equals f of a2, that means that a1 is equal to a2. So notice how this corresponds to our intuitive notion. Every input has exactly one output. So if we look at, say, two outputs that are equal, they correspond to the same input. And f is onto if and only if the range of f is equal to b. And as a reminder, the range of f is the set of f of a's such that a is in A. So we're looking at all the outputs of the function under f. Another way we can rewrite this, and this is just rewriting it from the statement over here, is that we say f is one-to-one. Another word for this is injective. If for each a and b in the set A, f of a equals f of b implies that a is equal to b. And so we see that that's exactly what is written in this portion here, where now we have the for each written out in English. A comma b now take the place of a sub 1 and a sub 2, and we're saying f of a equals f of b implies a is equal to b. But what if we were to take the contrapositive of this statement? Then the contrapositive is a sub 1 does not equal a sub 2 implies that f of a sub 1 does not equal f of a sub 2, or written differently, our statement 1 prime, we say f is one-to-one if for each a comma b in the set A does not equal b implies f of a does not equal f of b. So in a moment when we do get into proving statements, just keep in mind that whenever we want to prove that something is one-to-one, we have two ways of approaching it. We can approach it with f of a equals f of b, show that a is equal to b, or we can approach it as a does not equal b, and then we want to show that f of a does not equal f of b. Now for onto, we have another word that is oftentimes used, surjective. And so these words I will use interchangeably, as well as injective. So we say a function is surjective if for every b in b, there is an a in A such that f of a is equal to b. But that's coming from b being equal to the range. Since b is equal to the range, which is the set of outputs, that means that for every element b in the set B, we can find some input that maps to it. So we're gonna prove how this theorem, the definition that Velleman gives for one-to-one and onto, how that is equivalent to these in a moment. But first, I want to do some examples to get to familiarize ourselves with the techniques that we use to proving statements of the form: is the following function injective? Is the following function surjective? And so the last definition that I'll mention for this is the concept of a function that is both one-to-one and onto. So we say that if a function is one-to-one and onto, then the function is bijective. Another word commonly used is one-to-one correspondence. So let us look at a function that we have studied before in algebra. So we have a function going from the real numbers to the real numbers. It is defined by f of x equals 2x. And the claim is that f of x is bijective. So how do we show that this is bijective? So let's do some scratch work. So we want to show that it is both one-to-one, which I'm going to just write here as 1-1, and onto. So let's look at the case when f is one-to-one. So what we want to do by the definition, and the theorem, the equivalence, we have two methods. We start off with f of a equals f of b, and show that a is equal to b, or a does not equal b, implies f of a does not equal f of b. I'm going to approach it from the case of 1. So we're going to let a comma b be real numbers, and we want to show that if, actually let me write it like this, and assume that f of a is equal to f of b. And so now we have the premise of the conditional, and now we want to show is that a is equal to b. But now, f of a equals f of b, that's equivalent by the definition that we have up here, that f of x is equal to 2x, to 2a is equal to 2b. And that's just applying the definition of f. But now we can divide by 2. And then we have a is equal to b dividing by 2. And we are done. Now we have shown what we wanted. So f is one-to-one. What about onto? For onto, we need to choose an element in the set of outputs. In this case, the main thing is that the set of inputs and outputs are the same, so we have real numbers. But what we want to do is choose an element in the set of outputs, some arbitrary element, and find what is the corresponding element in the inputs that maps to it. So we're going to choose, let b be a real number. And what we want to show is that there exists some a that is a real number such that f of a is equal to that corresponding b. So now, once we show that a, we are done. Okay, so all we have is b is a real number. But we know how the outputs look like. So here is sort of assuming the conclusion. So we're going to work backwards. If f is onto, and so again, we're assuming conclusion here, but this is going to get us to what we want to show. Assuming conclusion. So not entirely precise since we're assuming what we want to show. If b is equal to 2x, then that tells us that x is equal to b over 2. So here's the proof that it's onto. Let a be equal to b over 2. Then f of a, which is equal to f of b over 2, is equal to 2 times b over 2, which is equal to b. And so now we have found the a that we want, and that a depends on b. But b was chosen arbitrarily, so we have shown that for any b in the real numbers, we can always find an a in terms of b, such that f of a maps to that b that was given. And so this shows that the function is bijective. So let's go ahead and now make this proof precise, because right now this is just our scratch work, so let's write a formal proof of this. So let's go ahead and show this proof formally. So it suffices to show that f is both injective and surjective. So we're going to start off by choosing a and b being real numbers, such that f of a is equal to f of b. Then, by definition of f, this is equivalent to 2a equals to b, and therefore a is equal to b. And now this shows that f is injective. And since one-to-one and injective are used interchangeably, I'm going to go ahead and use these words interchangeably throughout my lesson. So one-to-one and injective are the same words, similar to orthogonal, perpendicular, same meanings. So we have already shown that f is injective. So now let us show surjective. So next, let b be a real number. And so in our scratch work, we started off first by assuming the conclusion, and that's something you want to get in the habit of. In the scratch work, assume the conclusion, find that corresponding input that maps to that output. But when writing the proof, we go right to the output. So we have already found what we want. And so here, since a equals b over 2 is a real number, and f of a, which is equal to f of b over 2, which is equal to 2 times b over 2 is equal to b, we have that f is surjective, and consequently, f is bijective. And we're done. We have now proven that the given function is in fact a bijection. For our next example, we're going to consider the function going from the real numbers to the non-negative real numbers. So that's what this notation here means. And it is defined by f of x is equal to x squared. And what we want to prove is that f of x is surjective, but it is not injective. So let's go ahead and look at its graph. So we have here our favorite parabola. And to show that it is not injective, well, all we have to do is find a counterexample. Because to be injective is to say that every output has exactly one input. But if we look at, say, our points over here, so we look at, say, let's say that this here is 2, then we know that this is 2, 4, and over here we're going to have 2, negative 4. Sorry, negative 2, 4. So both of these have the output 4, but we have 2 inputs corresponding to it. So this is not injective. In our early education, at least in the US, this is usually referred to as the horizontal line test. And so we have that if we draw a horizontal line, it crosses two points, and so it is not injective. And so we get to see that. Now with surjective, we need to prove is that for any non-negative real number, we do have an input that maps to it. So what about that one? So let's do surjective. So let's choose a b that is a non-negative real number. Then we want to set b equal to x squared. So again, we're assuming the conclusion. And taking the square root tells us that x is equal to the square root of b, plus or minus. And now we have to only choose one. So we can take x is equal to square root of b. And here's where we use but here something subtle is happening. This is allowed because b is a non-negative real number. So note that since b is a non-negative real number, square root of b is going to be a real number. And so that's allowed. And so that's a crucial assumption. And so we'll come back to this moment in just a bit. So let's go ahead and write a formal proof of this. So proof. So we note that f is not injective since f of 2 is equal to f of negative 2, which is equal to 4, and 2 does not equal negative 2. And so that shows that it is not injective. Next, let b be a real number that is non-negative. Since b is non-negative, the square root of b is a real number. Now observe that if we take f of the square root of b, we have the square root of b, quantity squared, which is b. So f is surjective since b was chosen arbitrarily. And we're done. We have now proven this statement. Now, how do we just switch the question slightly to the following? So now we are looking at the following. So we have our function g. Now it's going from the real numbers to the real numbers, so that's the difference between this one. And in the first example, we had non-negative reals, but it's still the same parabola. G of x is equal to x squared. Now, in this case, the function is not going to be injective nor surjective. The injectivity, the failure of it, is the same as above. We have f of g of 2 is equal to f g of negative 2, which is 4, but 2 is not equal to negative 2. But for surjective, because now we have to take any real number b. But if we do the same argument we did here, when we take the square root, so we set b equal to x squared, take the square root, x is equal to the radical of plus or minus b, only defined if b is non-negative. So if b is less than 0, there is no x in the real numbers such that g of b, g of x is equal to b. And so that's excuse my handwriting, that's a no. So we cannot find a real number x such that g of x is equal to b. And so the part that we assumed here, that this is greater than or equal to 0, is crucial. And this touches upon a crucial aspect of functions that is different in how we perceive them in our previous courses. F of x is the parabola, but so is g of x. But they are not the same function because the outputs are different. The outputs here are non-negative real numbers. Over here, they are real numbers. And so for two functions to be the same, we must have that the set of inputs and the set of outputs are the same. Otherwise, we would have that this function here, f, is surjective, but then g is not surjective, and we want this property of surjective to be a property of the function. And so f of x is not the same as g of x. So for the next example, we have three sets, A, B, and C, given as follows. A is 1, 2, 3, B contains 4 and 5, C contains 6 to 9. And we want to know, is there some function going from A to B that is bijective? And the same from A to C, is there a function that is bijective? And the way we're going to go about doing our scratch work is by looking at a picture. So let's go ahead and view these three sets via a picture. And so here's the drawing. So here's a visualization. We have our set A, we have our set B, and our set C. So let's look at the first question. Is there a function from A to B that is bijective? Well, in order for that to be the case, we would need... Come on, get out. So here's our visualization. Here's A, here's B, and here's C. And we want to consider, is there a function from A to B that is bijective? Now, the way we're going to go about this is by doing the following. For a function f from A to B to exist, we need every input to be mapped somewhere, exactly once. And so we would need to map 1 to 1 of 4 or 5. We would need to map 2 to 1 of 4 or 5, and similarly with 3. But this is where we run into trouble, because now if we do a function going for, let's say that we map our element 1 to 4. We map our element 2 to 5. This function is, well, this is not a function, it's now a relation. Because in order to be a function, we also need to map 3 somewhere. But now 3 has to map to 1 of 4 or 5. And so there's going to be one output with 2 inputs. And so now 3 has to map to 4 or 5, so let's say that it maps to 3. So if that's our f, so f is now the set. If we think about this as a relation, this is the set 1, 4, 2, 5, 3, 5. Not bijective. Since the output 5 has 2 inputs. Of course, this is not a proof, this is just one example, but it gives us an illustration of how we should go about writing this up in just a moment. And so this is not going to be bijective because it is not injective. So it fails to be injective. Now, in the case of A to C, we see that we can take 1 and map it over to 6. 2, we can map it over to 7. 3, we can map it over to 8. But if we do so, it still leaves us with where to map to 9. And so now this function, if we let g be the function defined here, this is going to be an injective function. Every input has exactly one output. But now, for surjective, that is, onto, if we choose the element 9, there is no input in A mapping to 9. So this is not going to be surjective, therefore not bijective. 9 does not have an input mapping to this. So this function is not surjective. So what is going on? we have seen that there is no function that is bijective by looking at this example and extrapolating from that. That is not rigorous though. But I'm not going to show in today's lesson how to do this rigorously, because we are going to return to this once we cover the last section of chapter 5, namely inverse images. And with that notion, we're going to return to this and do it in a more general context. But one thing that we can see conjecturally from this example is the following. Let A and B be finite sets. Then there exists a bijection F from A to B if and only if A and B have the same number of elements. And so we're going to come back and prove this statement later in the course. And it is crucial that we take finite sets. As we will see, in the case of infinite sets, well, we first need to make a notion of what it means to have the same number of elements. And so that's the material of equinumerosity, which will be covered at the beginning of chapter 8. So now let us turn to proving how the original definition that Bellman gives for one-to-one and non-to is equivalent to the one we have been using for our proofs. But our definition for one-to-one and non-to was given symbolically in the following way. And so to prove the theorem, so let's go ahead and show one first. So by definition, we have that F is one-to-one if and only if not there exists A1 in A, there exists A2 in A, F of A1 equals F of A2, and A1 does not equal A2. Well, this is equivalent by the quantifier laws. When we have not there exists, this becomes for all A1 and then not this portion here. But then if we do one more, this will be not there exists, which is for all, and then not of this portion here. And so what that will give us is for all A1 in A, and then for all A2 in A, we have not F of A1 equals F of A2, and A1 does not equal A2. And so here, this is the quantifier negation law, which I'm running out of space, so give me one moment. But now if we negate this portion, we can apply De Morgan's law. And so now we have for all A1 in A, for all A2 in A. Now this becomes F of A1 does not equal F of A2, or A1 equals A2, De Morgan's law. But what is it that we want to prove? We want to prove something with a conditional. And a conditional, P implies Q, is logically equivalent to not Q or P. And so now we see that if we were to translate this, this will become F of A1 does not equal F of A2, or A1 equals A2, which is exactly what we have here. And so by the conditional law, we do have that these are the same. And so we're done. Conditional law. And so that takes care of the very first statement. And so now let's prove 2. So now we have, by definition, once more, we have f is onto, if and only if, and then we have the definition for onto. For B in B, there exists A and A, such that f of A is equal to B. But now, by definition of function, when we think about this in its set theoretic definition, that's the same as saying, when we say f of A equals f of B, that's saying that the ordered pair A comma B is in the function f. Since f is a relation, it is a collection of ordered pairs. So we got this here. But now, A comma B being in the function, and there exists an A, this here can be, by definition of the range of f, we can truncate this to saying for all B and B, B is in the range of f. And so we have for all B and B, B is in the range of f. And so we got this portion right here. And now what we want to show is the range of f is equal to b, but that's not quite what we have. We have that b is in the range of f. And since this is a for all b and b, we have that that's the same as saying that b is a subset of the range of f. And so now what we need to show to demonstrate the equality is that the range of f is contained in b. But now, by definition of range, we have that the range of f is the collection of all b in B such that there exists an A in A with f of A being equal to b. But then the range of f is automatically a subset of B since it's composed of elements of B. And since this is the case, now we have the reverse containment. And so now that finishes the proof. So thus, B is equal to the range of f. Now, a couple of things here in terms of the logical framework of this proof. We have shown that f being surjective is equivalent to B being a subset of the range of f. And so these are now equivalent statements. And since we have that the range of f is always a subset of B, we get the equality that is given here. And since everything is in terms of equivalences and definitions, we do have our if and only if statement. And so that finishes the proof. So we're done. So next, we are going to look at an example. So this is question number 9 from 5.2. And so we have A is equal to the power set of the real numbers, and we have that B is equal to the power set of A. So in other words, B is the power set of the real numbers. And we are defining a function from B to A by the following formula. F of a family of sets goes to the union of F. Now keep in mind, B is our set of inputs. So B is the power set of the real numbers. So in other words, the elements of B are the elements in the power set of A, but the elements in the power set of A are the subsets of the power set of the real numbers. So in B, we do have that the set containing 1, 2 and the set containing 3, 4, that is an element of B. So let's go ahead and just before we even tackle the question, let's get acquainted with this. So the set containing 1, 2, now this is an element of the power set of the real numbers. If we take the set containing the set 1, 2, now this is a set of sets, and this is going to be an element of the power set of the real numbers. Now, the set containing 1, 2 and the set containing 3, 4, so these are elements of the power set of the real numbers. But when we look at the power set of the real numbers, we can take the set containing both of these. And that's exactly what we're looking at. In this question, we're looking at the set containing 1, 2, the set containing 3, 4, and now this here we have an element of the power set of the real numbers, since the set containing 1, 2, set containing 3, 4 is a subset of that the power set of the real numbers. We do have that each of these is an element of the power set of the real numbers, so now the set containing them is a subset. And so that's the first test. It's just wrapping our minds around what this function even is. And so just keep this example in mind. So now let us use the definition of the function. F is defined as f of the family of sets is being sent to the union. So if we look at f of the set containing 1, 2, 3, 4, this is going to be equal to the union of these families of sets. But we only have 2 sets. So our family of sets this is our big F. So we're interpreting now our capital F to be the set containing 1, 2 and the set containing 3, 4. So in other words, we can think about this as A1, A2, where now this is A1 and this is A2. So when we take the union of that family of sets, we're just taking the union of 1, 2 and the set containing 3, 4. So we have 1, 2, union 3, 4. And so this is outputting back the set 1, 2, 3, 4. And this here is a element of the power set of the real numbers, because it is a subset of the reals. And so we do see that this here is in fact mapping to the power set of the reals. And so we have found what its image is, what it maps to. But is the function 1 to 1? Is it onto? So pause the video and give that a try. Experiment with it and make a conjecture. And if possible, find a counterexample, and when you unpause, I will work through this question and show how it is 1 to 1, to demonstrate if it is 1 to 1 or onto. Okay, so let's see. Is it 1 to 1? Well, if it is 1 to 1, that means that every output has exactly one input. So if we look at our output, our set 1, 2, 3, 4, is this the only set that maps to it? Well, by our construction, it's just the union of these. So if we were to have instead taking F being the set containing the set 1, comma, then 2, 3, 4, this will map to the set containing 1, union the set 2, 3, 4, which is the set 1, 2, 3, 4. So it is not 1 to 1. So F is not 1 to 1. Since the set containing 1, 2, 3, 4 has at least 2 inputs mapping to it. So that shows that this is not 1 to 1. How about onto? Is it onto? Well, if we wanted to find if it was onto, we just have to show that if we take an element of B, so let me go ahead and get myself some more space. So to see if it's onto, let us choose some set. Oh, A is already in use. Let's use capital X. So let's choose some capital X in the set of output, so an A. So X is in the power set of the real numbers. And what we want to do is find an element of B, so the power set of the power set of the reals, that maps to X. Now, at first glance, this seems like quite a task because the power set of the power set of the reals is immense. But all we have to do is find one thing that maps to it. And let's use our example here that we just did as a way of building intuition. So from that example, we have seen that the set 1, 2, and then the set 2, 3, 4 also maps to 1, 2, 3, 4. But what if we took f of the set containing 1, 2, 3, 4? So now this is a family of sets, but the family of sets has exactly one set inside it. So when we take it to the union, there's nothing to take a union of. This is just going to map to itself, to 1, 2, 3, 4. And that's the key. So we see that if we take the set of the set 1, 2, 3, 4, it maps to the set 1, 2, 3, 4. And so now we have X is in the power set of the real numbers. And what we are going to do is do the same example, but now put curly brackets on X. So let X be in the power set of the reals. Then F curly bracket X, so the set containing X, maps to the union of the family of sets, but there's only one set inside that family. And so this is just going to be exactly equal to X. And now, since X was chosen arbitrarily in the power set of the real numbers, we do have that this is surjective. So in particular, F is surjective. And we're done. And so when you're faced with a question like this, it is imperative to do some examples because it is easy to get intimidated. Because the power set of the power set of the real numbers, visualizing that is quite, it's a mess in terms of what is in there. But all we needed to do is make that realization that if we chose just any element in the power set of the reals, because the function is defined as the f of the family of sets goes to the union, we could use that to our advantage to show that it was surjective. And so we chose an arbitrary element in the power set of the reals. And now we show that this here maps to X. In chapter 8, when we get to infinite sets, what we are going to see is that the real numbers, of course, is infinite. But the power set of the real numbers is also infinite, but it's larger than the power set, than the actual set of the real numbers. And to make matters worse, when we look at the power set of the power set of the real numbers, that is larger than the power set of the real numbers. And so in this example, we are actually considering we have three different sets that are each a different size of infinity. And so we'll touch upon these notions and make them precise in our coverage of chapter 8. So the next result we are going to prove is theorem 525. And so now we have a function f from a to b, a function g from b to c. We have already seen that the composition is a function. Now what we want to do is if f and g are both 1 to 1, then so is g compose f. So let's go about doing the scratch work for this one. And then the second part is similar, but now f and g are both surjective, and we want to show that the composition also is. So let's look at 1. So we want to show that g compose f is 1 to 1. So what we need to do is consider A and B in the set of inputs, but the set of inputs is A, so we're going to say A comma B is an A. Actually, since we may have to use lowercase b later, let's use x comma y. So let's go ahead and say we have g compose x, g compose f of x equals g compose f of y. And by definition of 1 to 1, and the theorem we saw earlier, we want it suffices to show that x is exactly y. So how do we go about this? Well, we have g. By definition of this is g of f of x. And this is g of f of y. But now, we know that g is a one-to-one function. So that tells us that g of, say, u being equal to g of v implies that u is equal to v, since g is one-to-one. So if we think about this here as f of x being u and f of y being v, this is telling us that f of x is equal to f of y, since g is one-to-one. And applying the same argument, because by assumption f is one-to-one, that tells us that x is equal to y, since f is one-to-one. And so now that shows that g compose f is one-to-one, because that's what we wanted to prove. And so that's how we go about doing this proof for one-to-one. So let's go ahead and write this precisely. So let's go ahead and prove that first statement. So we have f is going from a to b, g is going from b to c. These are injective functions, so both functions are one-to-one. And we're choosing x, y to be in a. So we want to show that that the composition is injectives. So let's suppose further that g compose f of x is equal to g compose f of y. It suffices to show that x is equal to y by definition of one-to-one. So let's go about this. When we covered our definition on composition, we have already, this was theorem 515. So by theorem 515, we have that the evaluation g compose f at x and then g compose f at y, that this is equivalent to g of f of x equals g of f of y. So the theorem is being used in translating the composition g compose f evaluated at x to rewriting it as g of f of x. Now, since g is injective, we have that f of x is equal to f of y. Similarly, f being injective, implies that x is equal to y. Therefore, the composition is injective. And so we're done. So we got this part. So we still have to prove 2. So let's return to our scratch work. So for surjective, now what we want to do is take an element in C. So let's go ahead and let Z be in C. So we want to show that there exists some lowercase x in A such that g compose f of x is equal to z. But we do know that g and f are both surjective. So let's use that to our advantage. So g compose, so if we work backwards, so we want to find this x. That's the thing, we need to show the existence of this x. So the way we're going to show that existence is, since we're going to work one function at a time, since g is surjective, there exists some y in V such that g of y maps to z. And so that's just the definition of onto. If we know that it's surjective, that means that every element in C has an element in B that maps to it. And so the definition is giving us the existence of this lowercase y. Similarly, since f is surjective, we can find some x in A such that f of x maps to y. Because we know our y is in B, and f being surjective tells us that every element in B has an element in A that maps to it. So we have that existence of some x. So we have f of x equals y. But now we are done, because if we take g compose f of x, by theorem 515, this is the same as g of f of x. But f of x is equal to y, so we have g of y, which is equal to z. And now we have shown that this is onto. So let us write this up formally. So here we have the proof, the formal proof. So we're, again, taking f from a to b, g from b to c. These are surjective functions. We're choosing z to b and c. And since g is surjective, there is a y in B such that g of y is equal to z. And since f is surjective, there is a x in A such that f of x maps to y. Consequently, we are done, because now we have g compose f of x is g of f of x, which is g of y, which is equal to z. Thus, g is surjective. And we're done. And so that concludes it for today's lesson. In our next lesson, we're going to start investigating the next section. So this is the section on inverse functions. And so that will tie also with the topics that we have covered previously, but now putting it formally in set theoretic language.